Okay, so we have, I think we have talked about the membrane preparation by the phase separation or phase inversion, and you can make the symmetric membrane by evaporation. Okay, this is called the diffusion-induced phase separation, whereas you can make the symmetric membrane with a porous structure using if you put the membrane in the water, so that you can replace the solvent with the non-solvents. Okay? Then you can make the porous structure like this. And some of the examples of this, the porous structure, is made by the polyamide, polysulfone, and the PVDF membranes. And if you have a large porous sizes like this, you can remove the large molecules such as bacteria and viruses, so that you can use this for microfiltration and other filtration purpose. We can make the polymer membrane with a very defined structure by using template method or the block copolymers. Now, this is the example of making lithographic channels, and you can make the lithographed channel arrays by using the 3D dynamic structures. What it is that you have a polymer solution, and by making the imprinting technology, you can make the 3D very well-defined structures. And if you remove those structures, then you form a porous structure in the bottom, and these white structures are porous structures, and the dark ones, dark blue, is filled one. So you can make the just like a track-etched membranes. And this technology is currently applied to specific applications, but not general, because it's not easy to make a large scale, but you can make a very well-defined microfluidic applications, and some applications in a very small scale, but not in the larger scale because of the difficulty in making the larger membranes. This is one of the other examples of some examples like PEEK, polyether ether ketone, with inorganic material, and you can see it's like a well defined structure such as this, and this the structured membrane can be very ambitious in some cases, and if you have a very well controlled pore sizes with a very narrow distribution in size, then there's a lot of applications, just like I think I have mentioned to you about the track-etched membranes. And track-etched membrane has different in the spaces between the pores, but in this case, you have a very well-defined structure. So although this is the AFM image of the some of these structures, if this is true, then it will be very useful. But again, the manufacturing of this well-defined polymer structure is not easy, because one of the precursors for this structured membrane is a block copolymer, and as you know, the synthesis of block copolymer is not easy. But if you have a very well-controlled manner of synthesis of block copolymers, yes, you can make the polymer with a polymer membrane with well-defined structures. Another example is a symmetric membrane with a hollow fibrous configuration with well-defined pore structures. Although this is made of polypropylene, polypropylene could be fabricated into hollow fiber by using TIPS process. TIPS process will be touched in few minutes. But anyway, if you use some novel diluents at elevated temperature, you can make a PP membrane with the tips. Polypropylene is hydrophobic, so polypropylene hollow fiber is very useful in some of the applications. Now, Mitsubishi Rayon is making this polyethylene and polypropylene hollow fiber for microfiltration purpose and MBL, membrane bioreactor systems, and this is one of the examples. In the meantime, the polypropylene could be fabricated into the flat sheet by Celanese, and they could make a cell guard membrane with a pore structures like this. Okay? Of course, pore structure might be a little different depending upon the manufacturing processes. You see the micropores on the surface of the membrane, and you still have the micropores, although it is not seen in here. And also we can make the osmotic structures as well. Okay? Osmotic structure is defined as the different structure along the thickness gradient. Okay? Along the cross section, you will see the different structure from the top to bottoms. Okay? Now, in many cases, you will have a very porous substructure and very thin skin layer. And if this is combined, we call this as a composite membrane if you have two different polymeric structure with the skin and the substructure. But if you have a same membrane, same polymer with a different porosity, we call this as asymmetric polymeric membrane, such as the case of Loewe-Solley-Rajan polymers. So Loewe-Solley-Rajan outer membranes. Skin itself, selective skin is a real membrane where selectivity is coming from the skin layer, whereas the substructure doesn't really matter about the selectivity or the separation factor, because substructure will act as a mechanical support only. Therefore, the selective skin is the most important in the cases. We wanted to decrease the thickness of the skin because the thickness of the skin will act as a barrier for your transport. Okay, so we wanted to design this membrane with a very low thickness as possible, because the intrinsic transport property is coming from the polymer itself, but the flux or pressure normalized flux will be determined by the thickness of the skin. Okay? If you have a lower in thickness, just like the case of Loewe and Solley-Rajan, you can increase the permeance. Okay, permeance. Permeance is the thickness dependent flux, so that if you have a lower in thickness, then you increase your the permeance. Permeance is different from permeability because permeability is determined by the polymeric structure, whereas permeance will be determined by the thickness of the skin layer. So if you have a lower in thickness, typically in our membrane, the skin thickness will be around 100 nanometer, whereas in the case of gas separation membrane, it's about 40 nanometer in thickness of the skins. And so the skin thickness may be different depending upon the producer and depending upon your the applications. Okay, so we will talk about the osmotic membrane structure in detail. Now, if you're talking about the osmotic membrane, then we have two types. One is called integrally formed osmotic membrane made of the same polymer. Okay, just like a Loewe-Solley-Rajan's, so there was a triacetate the membrane. Whereas if you mimic this integral skinned osmotic membrane, you can have two different structure. One is the skin layer on the top, made of A polymer, polymer A, and you have a mechanical support made of the polymer B, but you have a larger porosity on the bottom. And so if you make a composite, then we call this as a composite membrane. So most of the outer membrane and most of the gas separation membrane is made of a composite membrane, because they usually coat the skin layer on the top, and in the case of gas separation, of course, you plug the defect from the polyether sulfone fabrication, and you coat those defect with the PDMS polymer. So the asymmetric membrane is a starting point of the development of membrane in ultrafiltration and reverse osmosis. But composite membrane is the major component of the whole market in membrane, particularly reverse osmosis and reverse osmosis membranes. Now, from now on, we'll talk about how we can make the membranes. Okay, you need to have a polymer, solvent, and additives. In the case of Loewe and Sori-Rajan's cases, or Wright and Bratton's case, they have a cellulose acetate. Acetone was used as a solvent, so the cellulose acetate is dissolved very easily in acetone, but they use the additive, the glycol, in some cases, into this solvent, so that they have a mixture of three components. Typically, it's a clear solution if it's the polymer dissolved in the solvent. This is what we call the dope solution. Dope solution is a clear solution, although you add some of the additives. Additives is very important. Choice of your solvent is, of course, important as well. If you choose the solvent with a very high volatility, such as a THF or acetone, you should be very careful, particularly the safety of your environment, safety of your the manufacturing site. Therefore, typically in industry, solvent should be non-volatile, highly porous, highly polar, aprotic solvents such as NMP or DMSO, DMAC, but not DMF, because DMF is very toxic. And in Europe, even the NMP will be banned, okay, and is now banning from the manufacturing site of these membranes. Okay? NMP was regarded as a very safe solvent because the boiling point of those polar and polar aprotic solvent is about 200 degrees C, close to 200 degrees C, so that at room temperature or at around 50 degrees C, it's not very volatile, so there is no harm to the human being, to the workers, to the manufacturing site, the operators. But NMP will be very harmful if you hollow or touch with your human beings. So the safety rules in Europe will ban the use of this NMP as the solvents in their own sector, but not in Asia or not in China and Korea. We can still use NMP, but I don't know when it will be banned in the future. Therefore, there's a lot of efforts to replace the solvents with the green solvents. That's why we are working on the 10th floor, just replacing the solvent. And yes, there are several choice of the solvents, but if you change your solvents, then full manufacturing process will be different. Membrane property will be different, so that you have to restart again of your membrane, the manufacturing properties. Okay, so, and the polymer concentration, particularly the polymer content in the solvent, will be very important finally into your the manufacturing of your the polymers, manufacturing of polymer membranes, because it will affect the formation of the macro voids, formation of defects, formation of your entanglements in the polymer membranes, final polymer membranes, and of course, finally the additives, type of additives, content of additives will be determining the final morphology of a membrane as well. So it's not that easy, although it looks very simple to make a membrane, to prepare the DOP solution and just to cast it, evaporate, or to coagulate them. But it was regarded as an art about 50 years ago. But right now, there's a lot of science in choosing the right polymer, right solvent, and right additives. So we will try to touch upon how we can make these fleshy membranes and further on the hollow fiber systems. Now once you prepare the DOP solution, easiest way of making the membrane is to cast. Okay, cast on top of your glass, for example, at different temperature. Okay? You can increase the temperature, you can decrease the temperature, and the temperature of your casting process is very important. Typically, it is cast at room temperature in the laboratory. So the polymer solution is the pour on top of the casting plate, typically the glass plate, and you just roll this casting knife, usually the Gano knife. The Gano knife can control the thickness of your the plate, so that this plate, the casting knife plate, will be moving up. If you control the thickness of your the space between the knife and the plate, then that will determine the thickness of the casting solution. Okay, after casting, and also with the same space between the knife and the plate, polymer concentration will determine the final thickness of the membrane, because if your casting solution thickness is such as this, final thickness of the membrane after evaporation, complete evaporation, depended upon the polymer concentration. For example, if you have a 20% polymer solution and cast the solution on top of the support, and if you completely evaporate, then the final thickness will be about 20% of the initial the thickness of the casting solution. So it will be about, if it's about 100 micron from the casting solution, final thickness will be about 20 micrometer. So this way, if you wanted to make certain thickness of your final polymer, then you will be able to determine what's the thickness of your initial casting solution. Okay? So by adjusting those thickness and concentration of polymer, you will be able to get the final polymer thickness. Now, if you wanted to make a non-porous membrane on the top and the porous membrane on the bottom, and this is what we call the integrally asymmetric membrane. And what you will do is that you first cast the membrane and evaporate for some time, evaporate the solvent for some time, and the time for evaporation will determine the thickness of the dense layer on the top. Okay? And after some time, if you put your total support and polymer solution or gel into the non-solvent bath, which is called the coagulation bath or precipitation bath, then there is an exchange between the solvent in the polymer solution and the non-solvent. okay, will be exchanged. So non-solvent will be coming and solvent will be going out if the solvent in the polymer solution will be soluble in the coagulant, okay? Typically water. So in this way, you can make the porous structure on the bottom and the skin layer on the top. This is how we can make a symmetric flashing membrane. And this way you can make the hollow fiber as well. You first make a dope, just like a flashing membrane, and put it into the reservoir. Put it into the reservoir of the dope solution is put into the reservoir. And if you pressurize this reservoir, then the polymer solution will be fed into the spinneret. Spinneret has two layers. One is the layer with the polymer, which is coming from the polymer solution is coming from the nozzle, whereas on the bottom, then there is a second bath with the bore fluid. So bore, typically the water, is fed into the core of this the spinneret. So the polymer solution and the bore is fed into the same spinneret. And when you come out through the spinneret, it's coagulated in the rotating coagulation bath. We have this is what we call the NIPS system. NIPS system, non-solvent induced phase separation. And this is a very typical way of making the hollow fibers. Of course, the distance between the spinneret and the coagulation bath is very important. This air gap distance is one of the parameters determining your final morphology. And the temperature of the coagulation bath is very important. The type of coagulant is very important as well. And the polymer solution content, polymer dope fluorate, bore fluorate, type of the bores, those were very important properties of determining your final morphology of your hollow fibers. This is not a very good picture. This is one of the example of your hollow fiber system. Then you have a fiber from polymer solution. This is from this is a hollow. This is a hole in the core side, and that's coming from the bore fluid. Okay? And if you enlarge the surface of this layer, you have a macrovoid. You have a macrovoid and a skin layer, and you have substructures. Again, I said this is not a very good hollow fiber, which is not used in the industry. The wall thickness ratio is very important as well. Wall thickness ratio is the one that you have an outer diameter and the inner diameter, and the ratio of the wall thickness is important because in many cases pressure is the driving force. So the pressure could be applied from the shell side, or from the lumen side. Okay? So if the thickness is very thick like this, I would say thickness ratio is about 10% or less, then it's not pressure resistant. Okay? So we have to have a certain the ratio of the wall. Typically, it's about 40 to 50%. So you should have a very large walls in many cases, because in the gas separation membrane, the pressure will be from 10 to 20 bars, so that it should be resistant to that high pressure. If you look at the reverse osmosis, then the pressure will be, several tens of bars, such as 50 bars or 40 bars, in some cases 100 bars. Okay? So you should have a certain thickness of your wall. if you're using this membrane for water, such as ultrafiltration and microfiltration, microfiltration has the lowest pressure driving force, which is about few bars, okay, 5 bars or 4 bars. Ultrafiltration maybe up to about 10 bars. So with this very thin skin layer or wall, there is no use in industry. Okay, so this was the case for NIPS, and we can talk about the TIPS. TIPS is the one that the temperature is a driving force inducing the phase separation, so that you can cool down from liquid to the solid phase. So by decreasing temperature from liquid to solid line, you can crystallize the polymer if it's a crystalline polymer. Therefore, the TIPS is typically applied for the polymers, ideally for the polymers with the crystallinity, at least the semi-crystallinity. If you have a 100% amorphous polymer, ideally it's not possible to make the membrane with the TIPS. Okay? So TIPS process needs the polymer with the melting temperature. Again, last time we talked about the melting temperature. Melting temperature is the temperature where your crystal melts. Okay? Okay? If you have crystals, we call that as a crystalline polymer, or at least a semi-crystalline polymer. Okay? So the polymer should have a melting temperature in TIPS process. And second requirement is that we should have a solvent, but we call this as a latent solvent. Latent solvent should be available. Okay? Latent solvent is very important in the TIPS, and this is one of the efforts at 10th floor we are working on. We wanted to replace NMP with some of the green solvents, okay? Because NMP still has the hazardous in nature. Therefore, we wanted to use the clean and healthy solvent or green solvent when you recycle them as well. We can make the hollow fiber, and we can make a flash sheet by using these TIPS, by casting or spinning. When you want it to cool, the cooling rate and cooling medium is very important to induce your phase separation. Latent solvent, okay, in the dope solution will be extracted. Right? So when you extract the latent solvent, it should be very important as well. Latent solvent for TIPS process of PVDF membrane has been the NMP or in many cases dioctyl phthalate or dibutyl phthalate. Those are the precisizers, and the melting point of those DOP or DBP was about 200 or over. So that if you add the PVDF in the DBP or DOP, then it will be very volatile at high temperature. Okay? So when you spin those the dope solution with the PVDF and DBP or DOP, it's volatile, so that you can smell those DOP and DBP, which is very hazardous and toxic and also carcinogenic. And it's not recommendable, of course, but still it's used in Korea, and of course used in many in China, and therefore we need to ban this use of these latent solvents, which are carcinogenic. And then finally you can dry this membrane or the fibers. This is the typical example of the TIPS membrane with the cross-section and the enlarged structures. I think this was manufactured at ITM with Professor Driolis. Alberto Figoli is in charge of this TIPS process, and you will see you have a very good membrane with you can have a porous structure, or you can have a non-porous structure depending upon how you spin these hollow fiber systems. One of the advantages of this TIPS process over NIPS is the high mechanical strength, okay? Because you can induce the crystallization by temperature differences, so that you can make a highly oriented, highly crystalline material, highly membrane using this semi-crystalline polymer. Okay? So mechanical strength of PVDF hollow fiber from Dore is up to about 12 megapascal in the tensile strength, which is almost double the mechanical strength of the common PVDF membrane made from other producers. What they have done was they spin the hollow fiber with the tips and at high temperature, and also they use a NIPS process. NIPS process with to make out the porosity, and the mechanical strength is induced by this the TIPS process. So NIPS and TIPS combination is very typical in the industry. If you want to describe this phase separation process, we need to know about the thermodynamic factor and the kinetic factors, just like the same as most of the chemical processes. Right? And although quantitative analysis is quite difficult, we can analyze this phenomena as a phenomenological way. Right? Phenomenological way is not the real theoretical treatment of this process, but we can have the results and come back and sit down and look at what happened. Right? And then you can analyze those systems in phenomenological descriptions. Phase diagram is very important for this thermodynamic description, and we will see how this phase separation will be treated as the kinetic parameters as well. First of all, tips. Now, this is the polymer concentration in the x-axis. Polymer concentration. Toward the right-hand side is high polymer concentration. The left-hand side is low polymer concentration, which is solvent. And this is y-axis is the temperature. So when you increase the temperature of your polymer with a solvent, of course, it becomes a liquid, right? When you decrease the temperature with a high concentration of a polymer, it becomes a solid. It will be cooled down to become a solid. Right? So this is a typical way. And as you know, it forms in many cases, forms the low critical solution temperature, so that we have a bimodal line where you have precipitation in your polymer solvent systems. Okay, so the line with the blue or green plot is the bimodal line. Whereas if you make a derivative of this bimodal equation with Gibbs free energy, the second derivative will be the spinodal line, and spinodal line is described as this line here, okay, with the red spots. Now, under this spinodal line is unstable region, whereas above this bimodal line is a stable region. And in between this bimodal and the spinodal line is a metastable region. So there is no the precipitation occurs between these metastable regions. Now, if you look at the points where we have B prime and B double prime, B prime has a high polymer concentration, then the higher concentration than B prime, so that at the same temperature, when you compare this B prime and B prime and B double prime, this is the polymer rich phase, and this is the polymer lean phase. So at room temperature, with a given with a different concentration, you have different phases. Now you can start from A point A. Point A is liquid phase, right? So polymer with a solvent is increased your temperature above the melting temperature, and you start from there, okay? From A point, right? When you cool down your polymer solution, it will become crystallized, okay? You start to crystallize, and pass it through this region, unstable region, and then finally reach to the point B, where point B is the membrane, is the point with the membrane formation. Okay? Now for this B point, you have 2 points, B prime and B double prime. It could be moved to if you remove the solvent, then it becomes B prime. If you remove the polymer, then it becomes B prime and becomes a porous structure. If you move to B double prime, it will become polymer rich phase, which is the skin layer or something. So this line at a given temperature T2, starting from T1, you make a membrane with porosity or skin layer. Now this point is called the critical point, where the bimodal and spinodal point will meet, and A point you start. Although you start from A, you need to pass as small amount of metastable region as possible to close to the critical points, okay? Because there is no precipitation in those phases. Now this is the general description of the two-component polymer mixture using the TIPS process. This is the phase diagram for the NIPS process. You usually have a polymer, solvent, and non-solvents. We have a bimodal line, just like the case of a TIPS. We have a spinodal line, and the stable region, unstable region, and metastable regions. Now, if you look at this ternary phase diagram, you start from 0% of your polymer through the 100% polymer here. So you have some lines, okay, with the different polymer concentrations. If you go from the bottom to the top, you increase the polymer concentrations. This is the 100% solvent. This is 0% solvent. So you start from this line with the without solvent through this 100% solvent. Okay? And the same is true for the non-solvent cases. So we start, if you put the polymer like 30% of your polymer and 70% of your solvent, the point will be about A here, because you start from 0% polymer up to around here. It's about 30%, right? 30%. This line is without any non-solvent, so this is 0% non-solvent. And this point is about 70% solvent cases. So A point is the one that you do have only polymer and solvents. When you have this point here, critical points, this has, let's say, about 20% polymer and about 10% non-solvent and 70% or so the solvents, right? So anyway, if you look at any point, you can determine the composition of a polymer, solvent, and non-solvents, right? Typically, when you have a polymer solution, spin from the or cast from your cellulose acetate and acetone, you start from A point, and after a few seconds, you put it into the non-solvent. Okay, you put it into non-solvent, which is water. Then you will follow this A line, starting from A line to B line, and finally you have B prime and B double prime with the polymer lean phase and polymer rich phase with a wide range of polymer the porosity. Okay? Polymer porosity of a membrane is determined by this B prime, and the skin layer will be determined by this B double prime. So by using this ternary phase diagram, you will be able to make the nice membrane with some structures. But this phase diagram will not determine the macro void, will not determine the finger-like structure or sponge-like structures. It will determine whether you have a very whether you form the skin layer or not, depending upon where you start from. Okay? Whether you start from this point, whether you start from this point, or whether you start from this point. Whether you follow this A-B line here, or you follow this path, or you follow this path. Okay? Will be determined by your operation parameters. Okay. Now the binodal point determination is very important. So typically in the laboratory, you need to determine the bimodal points by using the cloud points method. Okay? Cloud point method is the one that you first prepare the polymer solution with the stirring. Okay? And you start to drop the non-solvent as a drop by drop. Okay, the small amount of the non-solvent will be typically dropped. Once you drop slowly the non-solvents to the polymer solution, there is nothing happen initially, but after some time, after some composition, you start to have precipitations. But initially, once you form a precipitates, it will be gone. But after some time, it's completely precipitates to form the equilibrium. Okay? Now, that point is called the binodal point or cloud point measurements, and you can determine the cloud points. This cloud point measurement is very important to determine your bimodal points, and typically it's done manually, but these days there's a light scattering. The laser detects the time and the amount of your the non-solvent cases. If you so you can just stop the non-solvent addition, and you can determine the what is the amount of non-solvent added to your polymer solution, and that's the point where you determine these points. Okay? So by changing the polymer solution or the polymer concentration, you can determine the bimodal lines, and typical example might be the exemplified in here. This point has about, let's say, the polymer concentration will be about 9%, and solvent is about, let's say, this is about 89%, and non-solvent is about, let's say, about a few percent, like 2 or 3%. Okay? So this point can be determined, and you start from there. Then you add a small amount of the non-solvent, and you found the clearing points, and if you just change the clearing points by diluting this polymer, then you can determine the bimodal lines. Okay? And this way, by just changing the polymer concentration and adding the non-solvents, you can determine the clouding points and bimodal points as well. Again, we can describe this, the formation of the porous structures with the phase diagram under the condition of different temperature and the composition. That way we can separate the phases. Okay? However, this does not guarantee the what about the finger-like structure, and what about the sponge-like structures? What about the shape of the cavities? What about the shape of the pores? Okay? So phase diagram does not provide you the information about the finger structure or the sponge structures, because finger and the sponge-like structure or the pore size distribution will be determined not by thermodynamic factor, but by the kinetic factors. So this will be treated in different way. So diffusivity of the various components is the kinetic parameters, and the kinetic parameters will determine the finger-like structure or sponge-like structures, or viscosity of the solutions, or molecular weight of polymer solution, and the polymer contents. Okay, is very important for your finger-like structure or sponge-like structures, or the driving forces, or the chemical potentials. Those are the determining factors for your morphology of your final membrane. So we will talk about the formation of the macrovoids. Okay? Macrovoids. Macrovoid will be important for finger-like structures. Okay? Macrovoids are the ones that you serve such as this. Okay? This one here. This is the small finger. It's like a when you have a polymer solution or a rice cake, if you push the rice cake with your finger, you form empty spaces with a finger shape, so that they call this as a finger-like macrovoid. Okay? This macrovoid, in many cases, is detrimental to mechanical strength, because this is empty space, so mechanical strength is quite weak when you have macrovoids. But macrovoid may be okay when you use your membrane at low pressure. Okay? So it's not always detrimental, but depending upon the application, you need to induce or you need to reduce the formation of the macrovoids. So we will take a look at the formation of the macrovoids. Macrovoid starts to form as an initiator and propagates or growth. Okay? So we will take a look at how this macrovoid is formed. Macrovoid is formed because of the so-called instantaneous demixing process. Okay? Instantaneous demixing process. Demixing is some sort of exchange process. Okay, mixing is the one that you have the mixing of the solvent, non-solvent, and of course solution together. But you have a demixing between the solvent and non-solvent. So the enthalpy might be changing. If the enthalpy is equal to is greater than 0, then we have a high probability of making the interaction between the polymer and the interaction between the solvent is very high, whereas if the enthalpy change is low or negative, that means that you have a mixing, okay? Mixing between the polymer and solvents. If the enthalpy is large, then you have a demixing process. So, so we can take a look at the demixing process with the macrovoids. And this parameter, the demixing process, is dependent upon the interaction between the solvent and non-solvent. This is very important for your macrovoid formation. So we'll take a look at it. Now, when you have a polymer solution, okay, when you have a polymer solution from here, and when you meet the non-solvent from the top, in other words, when you cast your membrane, when you cast a membrane solution and put it into your coagulation bath, the front of your polymer solution, which is this one here, polymer solution front will meet the non-solvent. So non-solvent will be intruded to the polymer solution, and because non-solvent is not miscible with the polymer, it will aggregate together and gather together in the white form. And this is the initiation of your polymer, and it will propagate as time goes by, so that you form, I'm sorry about the color, but it will become larger in macrovoids, because non-solvent is intruded and exchanged with the solvent and non-solvent, and you form some sort of eye drops, and it will later become the macrovoids. This is what we call the nuclei formation and the growth to form these macrovoids. And we can describe this right in here. This is because of the mass transfer during the polymer the membrane formations. We can describe this mechanism of the macrovoid formation in this slide. And this was taken from one of the students in the laboratory. And what he has observed, the Jongmyeong has observed, was that you have a different polymer concentration, 15%, 20%, and 23%. Okay? And this is the right-hand side is a polymer solution, and the left-hand side is the water. So polymer solution was put into the two slide glass, okay, and the water is injected from the left-hand side, from your side, and the water will meet the interface. So once the water is met, then you form this black part, which is a coagulated part, right? Coagulated part. And as time goes by, from 1 second, 30 seconds, 51 seconds, you see the macrovoid is propagating and growing each other. At little high concentration, you can clearly see the formation and propagation of the macrovoids. And after the 30 seconds, you have macrovoid. Macrovoid is propagating, and so on. So this will later become a finger-like structure, whereas this one, in the interface between the non-solvent and the solvent, will be the skin layer. So the skin layer thickness will be determined by polymer concentration and the other kinetic factors. As you increase the polymer concentration further to 23%, there is no macrovoid formation, right? So macrovoid formation could be determined by the polymer concentration, which is the viscosity, as I said, and also the other factors such as the kinetic factors and so on. So he showed us that you can see the skin layers and so on. I think he didn't take a look at the SEM picture here due to the limitation of his availability of the SEM in the 6th floor. But I think he can, add these pictures in this way. We can see the video of you see when the water is meet with the polymer to the right hand side, you can see the propagation of your macro void as a function of time. Okay? You see, the macro, once it was formed, then it will be propagating in such a way that look at the formation of macro voids depending upon your polymer concentration, polymer composition, and it's very important to determine your skin thickness of your fresh sheet and hollow fiber systems. Okay, sorry. If we wanted to make the membrane with sponge-like structure, we can change the concentration to high concentration from the low concentration. So if you increase the concentration of a polymer, you can at least avoid the formation of the macro voids, because the entanglements between the polymer chain will prohibit the aggregation of your non-solvent into your polymer solution, so that there is no point of nuclei formation and growth of your the macro voids. Or if you add the solvent into the coagulation bath, okay, so if you add the solvent in the coagulation bath, you can reduce the non-solvent power of your coagulation bath, so that you delay the demixing, in other words, coagulation, during the process, so that it will slow down your demixing process. That will reduce the formation of the macro voids, formation of your nuclei, and the growth of your macro voids. Or if you add some additives to the casting solution and increase the solvent power, then you can reduce the formation of the macro voids. This is the way of making the sponge-like structure, or reducing the macro void formations. This is the typical parameter in the membrane hollow fiber systems to avoid the macro void formations. In the case of TIPS process, I think we have already talked about this. TIPS process. In the case of TIPS process, we need to think about the thermodynamic factors. Right? When you plot the Gibbs free energy of change of melting versus the composition, okay, composition of your polymer, Gibbs free energy of change of mixing, delta G is equal to delta H minus T delta S. When you wanted to make the polymer membrane, okay, for mixing, the requirement for this mixing is that delta G of mixing should be negative. If you define this delta G of mixing is equal to 0, then we'll reach an equilibrium. Okay? If delta G of mixing is positive, then the mixing is not possible. Okay? It's so when you wanted to induce your mixing process, then or spontaneously mixing, then delta G should be negative. In order for the delta G to become negative, delta H should be 0 or negative or as low as possible. Okay? Again, the enthalpy change, when you have high enthalpy changes between the two systems, polymer and solvent, it becomes, the polymer-polymer interaction and solvent-solvent interaction is high when delta H is high. Okay? When delta H is low, then polymer and solvent interaction is high. Okay? In other words, so, if delta H is equal to 0, then polymer-solvent interaction is equal. So delta H should be as low as possible, and hopefully should be negative. Okay? If you have a negative contribution of delta H, then it will contribute to the negative, the delta G, of course, right? And this is the minus T delta S. Okay? T, temperature, is absolute temperature, or Kelvin temperature should be positive. And delta S is usually positive because when you store your system, your entropy will be changing by the agitation and so on. So usually T delta S is a positive term, and you have a negative sign, minus sign in front of T delta S, which will contribute to your negative contribution of delta G. So the only thing is about delta H, and delta H should be the way when you have polymer and the solvent interaction should be negative. So when you plot Gibbs free energy mixing versus the X, which is the mole fraction or weight fraction or whatever, or the volume fraction or whatever, then your chemical potential will be changing, of course, and when your delta G of mixing is positive, this is toward the upward, and delta G of mixing is negative, then you have a negative contribution. So in many cases, delta G is following this line, this line, and when you plot with some composition x2, then this point will be the drawing the line over here, so that you can determine the chemical potential of each cases with the different compositions. So this is the basis of the temperature-induced phase separation, and we will, I guess, next time we'll talk about, on Friday we'll talk about how this the curves will be changing in thermodynamic way of mixings in the next slides, I guess. So again, we need to talk about starting from A point at T1, you stop your so you have a dope solution from A point, and when this dope solvent will be meeting with the coagulation bath at T2 at low temperature, you start to make a membrane with the B point, where your polymer dope composition will be determined in this way. So this is the basis, and we'll talk about the theoretical basis of the thermodynamics in the using of the Gibbs free energy mixing in next time. So so far, I think we talked about flat sheet and hollow fiber membrane systems, and we discussed about general description, particularly the phenomenological description of phase separation, particularly the tips and nips, and the importance of a macro void formation. Macro void formation is a kinetic factor, whereas so the kinetic factor will determine the macro void, and the macro void will eventually affect the finger-like structure and the sponge-like structure in your membrane configurations. Okay? So we can further discuss about the thermodynamics and the kinetic factors on Friday. Any questions or comments? If not, I think I will see you on Friday.